Again, my name is Dave Kroll from Imagine That. I'm very pleased to have Averill M with us, who will be talking about the critical importance of simulation input modeling. You should be seeing his first slide on your screen right now. Dr. Averill M is president of Averill M Law and Associates, a company specializing in simulation seminars, simulation consulting, and software. He has been a simulation consultant in numerous organizations, including Boeing, ConocoPhillips, Kimberly-Clark, M&M Mars, Oak Ridge National Lab, the U.S. Air Force, and the U.S. Army. He has presented more than 500 simulation short courses, which I recommend. I've attended a couple of them, in 18 countries. He has written and co-authored numerous papers on books on simulation, operations research, and statistics, including the book Simulation Modeling and Analysis that has more than 135,000 copies in print. He developed the Expert Fit distribution fitting software and also several videotapes on simulation modeling. He won the Informs Simulation Society Lifetime Professional Achievement Award in 2009. He has been a tenured faculty member of the University of Wisconsin-Madison and of the University of Arizona. He has a PhD in industrial engineering and operations research from the University of California at Berkeley. So Averill, I'll send it over to you. Again, if there's questions, please type them in, and I will do my best to answer.
Well, good morning, everybody. Can everybody hear me, hopefully? This is the first time I've ever done a webinar, so it's kind of strange just talking to the computer screen. But I guess we're ready to get started here. Because this is a new experience, I don't know exactly how the timing will work out, although I have given this talk a few times at conferences where it took 1 hour, which is about where we want to be. So anyway, everybody sees the title there, and now I will go to the table of contents, or the outline, I guess I should say. And so we're going to look at some examples of real-world data sets. We're talking about input data sets used to build a simulation model. We're going to talk about the importance of using, so to speak, the correct distribution to model a source of randomness in your simulation model. We're going to talk about methods of representing randomness in a simulation model. And the main part of the presentation, where most substantive, is that if you have data that you've observed and you want to fit a theoretical distribution to it, how might you go about this? All the formulas for hypothesis tests or goodness of fit tests or graphs, they're all in my book if you want to explore them. All the graphs and statistical methodologies I developed for this presentation using Expert Fit. So we're going to start out with some examples of real-world data sets that have come from various simulation projects. Here's one that I got from the U.S. Navy. They're looking at weapon systems aboard a ship, a particular component thereof, and these data correspond to repair times. We have 122. Here you see a histogram. On the y-axis, you got proportion. And this is positively skewed since it has a longer right tail. If you go through a fairly exhaustive analysis, it turns out that the log normal distribution does provide the best fit. And by the way, ExtendSim does have about, I think it's about 32 theoretical distributions that are built in for your use. The next data set comes from an automotive manufacturer. Here, once again, you see skew to the right, and also the histogram is shifted away from 0. These are processing times. I can't tell you the name of the company. It's one of the big 3 automakers. It's not Chrysler or Ford. That's all I can tell you. Okay. And here the best fitting distribution is a beta. Next we have interarrival times, which is something that's widely modeled in simulations. These are actually interarrival times of cars to drive up bank over an hour-and-a-half period. This actually came from a student project at the University of Wisconsin-Madison. And here you can see that the histogram has the exponential-like shape for density, the exponential density, skewed to the right, and not surprisingly, exponential provided the best fit, and also you couldn't refute the fact that it was a good fit for these data. And then we have something somewhat different here. These data are actually negatively skewed. Some number of years ago, we did a number of projects for Kimberly-Clark, and these are what are called parent roll data. They make these large rolls of paper up that are about 8 feet in diameter, and then they're cut up into smaller pieces to make, say, facial tissue or bathroom tissue. And the issue here was how many yards of paper on one of these rolls, and the question is, why is it skewed to the left here? And one of the things I always recommend is that you don't want to just take the data as abstract numbers. You want to understand the process that produced the data. The reason it's kind of cut off here on the right side is that the rolls cannot be too big because the rolls are put on the spindle of a machine, which cuts the rolls up into smaller pieces, and if the roll is too big, it won't fit on the spindle. So that puts kind of an upper bound on the right side. And as far as the left side goes, when they're rolling these rolls, sometimes they break and you lose paper, and so it tails off to the left. And the Weibull, which is one of the few distributions that could be skewed to the left, provides a good fit here. And then lastly, we have the data set we'll actually analyze here in class, so to speak, in some detail. These were loading times for oil tankers, for ConocoPhillips. And here we had 856 observations skewed to the right. The log logistic provides the best fit. You might say, log logistic, well, how am I going to use that? Well, amazingly, that is built into ExtendSim, so you do have it available at your disposal. And here we see, everybody's heard of the normal or Gaussian distribution, and many people just use it because they say, well, I learned about it in my statistics course. But as you saw, there was nothing that was really symmetric. Matter of fact, I have more than 100 sets of data on my computer. None of them from an actual simulation project are normally distributed. Matter of fact, you could say with some honesty that the greatest application of the normal distribution is writing statistics books. Okay, I'm expecting here some laughter there. Okay, so now we go on to the importance of using the so-called best distribution. And I have 2 pitfalls that I'm going to discuss. And altogether I have 22 pitfalls in simulation modeling, and these are 2 important ones. The first one I'm going to discuss is that you have a source of randomness in your system or process. And rather than actually use a probability distribution to represent that source of randomness, you just use a mean. Every time you would need, say, a service time, you just use what you think is the mean value, your perception of the mean. Okay, now why would someone do this? Well, maybe you don't have enough data to actually determine what the distribution should be, or maybe you just don't realize that using the mean, using a distribution rather than mean is actually critical. So let's see what the pitfall here is in terms of a simple example. You have a single server, which could be, say, a machine in a factory. And let's suppose that the mean time between arrivals of customers is 1 minute, and the mean service time is 0.99 minute. And so if you computed it using a little queuing theory, it would turn out the utilization factor of the server would be 0.99. In the long run, the server will be busy 99% of the time. So we would expect the system to be busy, at least on the surface here. And we're going to look at 2 different versions of this. Case 1, we'll assume that the interarrival times are exponential with a mean of 1 minute, as stated on the previous slide. We'll assume that the service times are also exponential with a mean of 0.99 minutes, as on the previous page. And if you're to take a course in queuing theory in the university, this is what's called an MM1Q. M means exponential here. So the first M is exponential interarrival times, the second M is exponential service times, and we have 1 server. M is for Markovian, by the way. Now, since this is a nice simple system and everything's exponential, you can actually analytically compute performance measures. And it turns out that in the long run, the number in Q is going to be random. And on average, it's amazingly 98 jobs will be in Q on average because the utilization factor is so close to 1. Now, let's suppose your manager says on Friday afternoon, I want you to build a simulation model list, have the results on my desk Monday morning, first thing, but you want to play golf over the weekend if that's of interest to you. And so you say, well, I got to get this done quickly. I'll leave out the distributions. I never like distributions anyway. I'll just put in mean values. That ought to be good enough. So what you do is you make every interarrival time exactly a constant 1 minute, matching up what the assumption is, and then you make every service time a constant 0.99 minutes, matching up what the assumption is. So hey, this ought to work great because I got the means captured exactly. So you run the model, and it turns out that no one is ever in the queue, okay? And so I'll ask you the following question. Let's suppose you're doing defense work. Is 0 close enough to 98? Well, sometimes when I'm at military bases, people jokingly say yes, that's close enough. So anyway, you can see that you're getting something vastly different than what in fact is the true answer. And the reason here is you're not modeling the randomness. You got to capture the randomness, the variability, not just the mean. With the way we did it here, using just the mean values, the first customer arrives at 1, departs at time 1.99, the next customer arrives at 2, etc. So every customer arrives to find that the previous customer just left. A trick question here. What will the in which of the two cases will the throughput be smaller? Throughput is long-run departure rate. Well, turns out no difference. As long as the server can keep up with the arrival rate, the departure rate or the throughput will be equal to the arrival rate, which is 1. So once again, just getting the means right is not sufficient. We also have to capture the variability in the input processes. By the way, I have 173 PowerPoint slides. You think that's too many? I'm just joking. Okay, moving on. So now we come to the second pitfall. So maybe you feel, okay, now I guess I should use a probability distribution to represent a source of randomness, but does it really matter which one I use? You know, I've used normal distribution for years because I learned it in statistics. What's wrong with just using normal? Well, we're going to address that in this example. I'm going to take a little bit of water here. Let's suppose, once again, we have the single server queuing system. And let's suppose the interarrival times are exponential. That's fixed. And we have 200 observations we've collected on service times. And we're thinking about fitting these 4 distributions in turn to these 200 service times and then using one of the fitted distributions. All of these, once again, would be available in ExtendSim. Now, if you're not familiar with these distributions, let's just go take a quick look at them. First of all, we have the Weibull here, and this is a very valuable distribution. It can take on different shapes, but one of the very useful shapes here is skew to the right. Okay, then we have the exponential, and that's the familiar exponentially decreasing shape of the exponential density. Here we have the famous but not that commonly occurring normal distribution, symmetric about the mean. And then lastly, we have the log normal. It looks something like the Weibull and, for that matter, the gamma, but here it can rise away from 0 more steeply and have a longer, thicker right tail than those other distributions. Okay, let's go back to where we were now. And let me just give you a little bit of an idea here. What does fit mean? We'll talk about that more later on. Let's say you wanted to fit a normal distribution to your 200 data points, and you made a histogram of your observations. Very, very roughly, you could think of fitting a normal as follows. A normal has a mean, mu, and it has a variance, sigma squared. You could say, well, how should I pick the mean and the variance so that the resulting normal density looks most like the histogram of our data? Now, that's a very, very rough explanation. Okay, here is, in fact, the blue vertical bars, here's a histogram of our 200 service times. And you can see, in fact, that it is skewed to the right. And we tried fitting each of the 4 distributions to these data. And you can see that the histogram is a graphical estimate of what the underlying density is from which the data actually came about. And the exponential certainly doesn't look like this histogram, nor does the normal, which is completely symmetric. The 2 fitted distributions that look the most like our histogram are, first of all, the log normal in green there, but you see that it actually rises away from 0 here too steeply and actually misses here on the left. And also the log normal, the green one, has too long and thick of a tail as compared to the histogram. The Weibull, on the other hand, matches up really quite well. And if you did an exhaustive analysis with 25 different distributions, you wouldn't be able to find one that fits any better than the Weibull. And this is, among all Weibull distributions, this is the best fitting one. We'll talk more about that sort of thing later on. Now you might ask, well, okay, great, the Weibull is the best fitting one. But does it really, how much difference does it really make in practice, whether I use the Weibull or the ubiquitous normal? So we're going to address that here on this next slide. And so what I did here is, once again, okay, we're looking at the single server queue. The interarrival times are fixed as being exponential. And the question is, what is the effect of changing the service time distribution? And what I actually did here is made 4 simulation runs, each of length 100,000 customers. And in this table, I'm looking at the average delay in the queue only for each of these 4 candidate fitted distributions. Now, as we said before, the Weibull provides the best fit. For the Weibull, the average delay in queue over the 100,000 customers is 4.36 minutes. Now, you would think that that should be pretty close to the real system's performance, because the Weibull is the best fit. What if, on the other hand, we use the well-known normal? Well, surprisingly, we get 6.04, which is actually about 39% different, shockingly. So whether you use the Weibull, which is the best fit, or the ubiquitous normal, does make a difference. Now, to be honest here, this is a made-up example. Okay, so rather than say 39% error, it would be more appropriate to say 39% different. Okay, and let's even go further. Let's take the log normal. And here we would get 7.19, which is actually 65% different than the Weibull, even though they both have roughly the same shape. And the reason that the log normal delays are so much larger is that the log normal has that long, thick right tail. And so occasionally you're going to get those very big service times, which will tie up the server, causing a big queue to develop and customers having large delays. So in summary, the choice of a distribution does make a difference. One of the fundamental parts of doing a sound simulation study is modeling the system randomness using an appropriate distribution. Other important things are making sure that you try to validate your model, and then also, once you run your model and you get output data, making sure that you properly analyze the output data. Okay, moving on now.
Averill, if I could interrupt, there's a couple questions here, and this might be a good point.
That's the answer.
I'm sorry?
7 is the answer.
Okay. First of all, I am getting smiley faces when you make a joke, so people are laughing. They're just unable. You're unable to hear them. A couple questions that came in. One I'm going to defer until the end, but a couple I think might fit in here is, can you comment on using, if it is useful to force limits on a distribution based on the maximum and minimum obtained from data analysis?
From data, oh, okay, I can see what, I understand. So, and there's kind of a part 2 to that. So if you're fitting something like a log normal, potentially you could get extremely large values, say beyond the range of your data. Also, if you were talking about something like a service time at a teller in a bank, maybe you know no one in the history of the world has ever had a service time more than 15 minutes. Well, it turns out you can actually truncate distributions. You know, you could use one of these fitted distributions, but you can, I mean, a simple way to do it is that if you generate a value, say, bigger than 15 minutes, you just throw it away and generate another one. But I would defer you to the definitive reference, Law 2007 textbook, and in there's a section in Chapter 6 on truncating distributions. Sorry to do that, but that's where the formulas are. So go to your local library, then you can get it for free. Okay.
And actually everyone should have a copy of your book. Is it a good time to ask another question?
Only one?
I wait until the end.
Okay, good.
Okay. Averill, I've got one more question.
You have another one?
Yeah, or would you rather I wait until the end?
Well, we shouldn't have, let's say, we shouldn't have too many, otherwise we might run over. Let's try one more right now.
Okay. Can you comment on using empirical distribution in simulation? What are the implications of using an empirical distribution instead of other distributions such as exponential, assuming exponential distribution fits the data?
Okay, so the general question is, should one use a fitted theoretical distribution such as exponential, gamma, Weibull, or should you construct an empirical distribution from your data, both of which are supported by ExtendSim? I will actually get to that shortly.
Okay, I think I'll leave the other questions until the end. So there will be others coming in, but I'll wait until the end.
How many people do we have in the group now?
Try to look. 70. So.
70?
Yeah.
Okay, great. Okay, so now we're actually going to get to the point that was just asked by that particular person. Section 3 here is called, amazingly, Methods of Representing Randomness in a Simulation Model. And we're going to look at two cases. The first case, which you hope you will be in, is where you can actually collect system data. So for example, you might have an existing manufacturing process, and you could go down to the factory floor, and you could stand beside the machine operator with your stopwatch and collect processing times. Or maybe you have data on time to failure of some machine, time to repair. Okay, now, we're going to assume that standard assumption in basic statistics is that your data are independent of each other and also identically distributed. Identically distributed means they all come from the same underlying distribution, and that's abbreviated IID. Another name for that in a statistics course would be a random sample. Strictly speaking, I mean, if you want to be 100% correct, some of these methodologies wouldn't be applicable to simulation output data that aren't independent, but some people might just ignore that. Anyway, so we have these data x1 to xn, and for sake of our discussion here in, quote, class, let's suppose that these are continuous data, service times, repair times, whatever. We can also discuss the discrete case, but we don't have time, and in some sense as well. It's not as commonly occurring, and it's less interesting. Okay, now, given that you have data, what are the two main methods for representing that source of randomness? Well, the first method is we fit a theoretical distribution such as exponential to the data, and we're going to discuss in more detail. I mentioned it briefly or discussed it briefly. We will discuss in more detail exactly what that means. In fact, what most people would do is use what's called the method of maximum likelihood. So if you can find a distribution that fits your data well, like exponential to those interarrival times of cars, then what will happen in your simulation if exponential is for interarrival times, every time you need an interarrival time, you'll take a random number and randomly generate a value from the exponential distribution. Of course, ExtendSim is going to do that. You don't have to actually generate the random numbers between 0 and 1. So that's the first method. Okay, what are the drawbacks of this method? Well, first of all, you cannot always find one of these standard theoretical textbook distributions that provides a good representation for your data. I mean, these distributions to some extent have been thought up by perhaps a professor sitting in his office at a university, like Weibull was thought up by a Swedish reliability engineer in about 1937. He says, oh, that's kind of a nice formula. I'll call it a Weibull distribution. So the point being, why should any phenomenon in the real world that's random, why should values from that necessarily be fit well by one of these theoretical textbook distributions? Just kind of a rough number based on, looking at hundreds of data sets over the years, maybe 1/3 of all data sets you will not be able to find a good theoretical distribution. And in that case then, at the minimum, I would use an empirical there. Some other possible reasons that no theoretical distribution might work are that you might actually have data from 2 or more heterogeneous populations that have been mixed together. So you have a very weird looking histogram, and none of the standard distributions are going to fit well, most of which only have a single mode or hump. And then you also might have rounded data, like in a factory, maybe processing times have been rounded to the nearest 30 minutes, effectively discretizing the data, and no continuous distribution fits. By the way, at the rate I'm going here, it's going to take probably about 60 minutes, so unfortunately. 60 minutes, 70 minutes, so I might have to speed up or leave some things out. Okay, now here is some people's favorite method that was just mentioned, an empirical distribution. So rather than using one of the fitted theoretical ones, we're going to take our data and construct a distribution kind of directly from them. This is typically called an empirical distribution function. And just a review on what is a distribution function. If you have a random variable capital X, note up there at the top, the probability that the random variable x is less than or equal to some real number little x, that's called the distribution function or the cumulative distribution function evaluated at little x, and it's denoted by capital F of x. And we're going to approximate that by an empirical F tilde. And let's see how that's computed. Okay, so let's suppose we have some data x1 to xn. We take these data, we arrange them in increasing order. These are called order statistics. X sub 1 in parentheses is the smallest value. X sub 2 in parentheses is the second smallest value. Let's suppose that U is a random number. It's distributed as a uniform distribution on the interval 0, 1. And for sake of discussion, let's suppose we have 6 observations. And the way that the empirical F tilde is usually constructed is as follows. At the smallest observation right here, we define this to be 0. Now we have 5 more x's. So what we do is we jump up by 1/5 at each successive observation. So this will be 1/5 or 0.2, 2/5 or 0.4, and so forth. We end up with 1 here at the last observation. We connect those points by straight line segments, so we have a piecewise linear distribution function. To randomly generate from this empirical, we generate a random number u, which will be equally likely to be between 0 and 1. We come across, we look at where it hits the blue curve, and then we come down. We're linearly interpolating because we're assuming we have continuous data. And you can show that that red capital X does in fact have the distribution F tilde. The method that's being used here, by the way, is what's called the inverse transform method. And one thing about this particular methodology, which is widely used, is that if U is equal to 0, you generate the smallest observation, and if U is equal to 1, you generate the largest observation. So you can never generate anything outside of the range of your data, which is really kind of unfortunate, because what if your true underlying density has a long, thick right tail, and you have a relatively small sample? Then these observations are going to tend to be in the middle of the range of the density, above which the density takes on large values, and you may have never generated anything out, say, in that right tail. And if you're talking about a service time distribution, if you don't generate these big service times, then you're going to probably get delays or times in the system that are going to be somewhat smaller than they really should be. So the major drawback of using empiricals, which I consider to be a major drawback, is you could not generate values outside of the range of the data unless you have very large sample sizes. Another drawback is that if you have a large sample size, let's say 1,000, then you're actually going to have to enter 2,000 values into ExtendSim, and hopefully you can paste that in. But so what some people would do in that case is approximate that empirical F tilde by a distribution function based on a histogram, but then you're introducing error. To be honest, no one has ever done a definitive study to say absolutely which method is best and in what circumstances. Personally, I prefer fitting a theoretical if I can do it. If I can't find a theoretical distribution that works well, then I use an empirical. And you might ask, how do you know if you have a good fit? And we'll talk more about that later on. I guess we're actually about the halfway point now. Okay, now let's talk about the case where you don't have any data. I'm going to take another drink of water here. So you have a source of randomness in your system, like say processing times for a machine, time to failure, whatever. And let's just suppose it happens to be a task time and it's a continuous random variable. Now, many times, unfortunately, you don't have any data. You're talking about, say, a future system that is yet to be built. Or conceivably, like in semiconductor manufacturing, you might have 500 process steps. So you could have 500 service time distributions. You don't have the time to collect that many data sets and actually analyze them. So in some cases, most notably when you don't have any data at all, you're going to have to do something other than fitting distributions. This is not a substitution for laziness, though. A fundamental part of a simulation study, if you can do it, is, in fact, to collect data and try to find an appropriate distribution. So what do you do if you just can't get any data? Well, what most people do is use a triangular distribution. And you get the parameters you need by soliciting one or more subject matter experts. And let's look at the picture here. Okay, so we're talking about the task time. You go to the subject matter experts and you say, if everything went as well as possibly could, what would be absolutely the minimum time to do the task? And they might say A equal 2 minutes. And then you ask them, if everything went as bad as it possibly could, all of Murphy's laws are in effect, what would the time be? And they say B minutes, maybe that's 11 minutes. So now you've identified this interval, 2 to 11 minutes, where you think with a probability close to 1, this random task time is going to fall. Now we're talking about a continuous random variable, so we have to put a density function on the interval A to B. And the most common thing to do, as I said before, is to use a triangular distribution. And we need one more piece of information, namely the mode or the most likely value, that value above which the density takes on the largest value. And to make this a legitimate density, you have to pick the height so that the area under the density, as with all densities, is 1. And once again, this is built into ExtendSim, so in some sense, using it is not any different than using an exponential. And here we are in Simulation Methodology 101. I have a question for you. Can you use the mean rather than the mode? And the answer is, in general, no. You do need the mode. I won't go into any detail, but you really do want the min, the max, and the most likely value. And if you were trying to get this information from a machine operator, for example, in general, they probably wouldn't know the difference between the mean, the mode, the median. So you probably want to ask engineers. Anyway, okay, some drawbacks of this. One would be, how do you choose the value B, the maximum? Is this the maximum over the next 3 months or the maximum over a lifetime? Also, in practice, many times histograms of data are going to have a long, thick right tail looking something like a log normal. Like, for example, repair times for a piece of equipment will oftentimes have a long, thick right tail. And you're not going to be able to get the triangular distribution to look like that. Now, I did have a pitfall here, or talk about a pitfall, which is using the triangular distribution. I think I'm going to hold off on this to make sure I have enough time. But let's just say that, okay, if you look at the red there, okay, that's actually a log normal distribution. Let's suppose that was service time, but you don't know it, and you try to approximate it by a triangular distribution. You're just not going to be able to find a triangular distribution that works very well. Here's one possible triangular, here's another one. And the errors are going to be quite large. We can go over that in more detail after class in the hall. Okay, so I'm going to skip this for right now, and if we have time, we'll do it at the end. Okay, so the conclusion, though, is that it's imperative to collect system data, if at all possible, and to choose a corresponding distribution carefully. You don't want to be lazy and just say, I just use a triangular distribution because it's quick and dirty. Okay, now we're going to go to the subject of fitting a theoretical distribution of the data. If we go back to the main topic, which is where you have data available, the two main approaches, again, once again, are fitting a theoretical distribution of the data or using an empirical. Different people prefer a different choice. Personally, I like the idea of fitting the distribution. The empirical has this big problem of not being able to generate data outside of the range. Now, if you have a large sample size, the empirical will provide a good fit, but then you have the problem of getting it into the computer. There's not too much, though, to say about the empirical. I mean, I gave you the most common method for constructing one. So let's talk about how you might fit a theoretical distribution of the data. And I'm going to talk about a three-step approach, which is delineated in some detail in my book. And by the way, Dave said that most people have a copy of my book, but that's not nearly sufficient. I recommend 3 copies, one for home and two for the, one for the office and 2 for home. One's for the nightstand and one's for the bathroom. And also they make great Christmas presents. This is all just a joke, as I'm sure you know. Anyway, moving on to statistics, which is much more fun. We're going to talk about a 3-step approach here. And before we do that, we're going to have kind of a step 0, an exploratory step, which was where we're going to look at our data. We're going to summarize it and see what kind of insights we can get. And the first thing most people would probably do is take the data and summarize it. And in a basic statistics book, these would be called descriptive statistics. So we're going to look at things like the sample mean, the sample variance, and so forth. And let's take a look at that right now. What we're going to do is we're going to take the ship loading data, time to load an oil tanker, that was from a project at ConocoPhillips up actually in Anchorage, Alaska. And we had, as we mentioned before, 856 ship loading times. The minimum was about 0.37 day. The maximum is 2.18 days. So clearly they're positive data. The mean is 0.84 day. And which of these descriptive statistics here might give us some insight about the underlying distribution? Well, actually, probably in some sense the most useful one is the skewness, which you may or may not be familiar with. The skewness is computed from the data. It's a third moment, like the variance is a second moment. And if you have a symmetric distribution like the normal, the skewness is 0. If you have data with a longer right tail as far as a histogram, the skewness would be positive. So this indicates that the underlying density is skewed to the right. Also, if you have a distribution that's skewed to the right, usually the mean will be bigger than the median. The median, as I'm sure everybody knows, is the 50th percentile. Also, very definitely, you want to look at a histogram. Now, a fundamental question with a histogram is how many intervals do you need and how wide should they be? Generally, we'll make them the same width. Now, there is, regrettably, no definitive simple formula for choosing the interval width or the number of intervals. John Tukey, who has now passed away, one of the most famous statisticians, he had a book called Exploratory Data Analysis, and he recommended trial and error approach, which I do also. You want to take the smallest interval width that gives you a reasonably smooth histogram. This is trial and error. If 2 different people looked at a set of data, they would inevitably probably pick a different interval width. Okay, now, here's the histogram that I ended up with here. This was not something that I got the first try. trial and error. I ended up with an interval width of 0.1, and I guess here I had 22 intervals. And let me show you what I mean by trial and error. So I'm going to go over here to expert fit, and I have this set of data loaded in. I'm going to make a histogram. Actually, here I had 23. It doesn't really make a difference. Here's our histogram. Now, if you come up here to these little buttons here, and if I click on the left one, that will decrease the interval width by 5%. So let's do that here some number of times. And we eventually get the famous jagged distribution. Here we've made our interval width too small, and so the variance of the number of points in an interval is very large, and we get this jagged or ragged histogram shape. So that's not good. Okay, now let's go the other way, increasing the interval width by 5%. And we keep going, and we get the famous block distribution there. Here we've over-aggregated our data. We have low variance but large bias. And so we basically want to ramp down trial and error subjectively until we get an interval width where we get a reasonably smooth histogram. And we'll go back to 0.1, which is what I decided on before. So anyway, that's how I got the histogram. Now we go back to the PowerPoint slides, and I'll take another little drink of water. And once again, by the way, as Dave said, these slides will be posted, so you don't have to be madly taking notes. Okay, so we did the exploratory step, look at the histogram and some of the descriptive statistics, and those tell us that the underlying, and these are real data, these are nothing that were made up. The underlying data would appear to come from a distribution that skewed to the right has a longer right tail. So now we come to the first of our official 3 steps here. And from our exploratory step, this would suggest certain distributions that we might consider. For example, what distributions are positive or non-negative skew to the right? Well, distributions like gamma, Weibull, log normal, Pearson 5, Pearson 6, log logistic, all these are built into ExtendSim. I would not be considering the normal here, because the normal takes on values from -infinity to +infinity, and having something like a ship loading time of -2 hours, well, that's probably not too good. Okay, now the question is, how do you go about, we got these candidate distributions. Each of these distributions has some number of parameters, which generally speaking, the parameters can be classified to be either a scale parameter, let's start back a minute here, either a location parameter, scale parameter, or shape parameter. How do you determine, let's say we're talking about a gamma, how do you determine the optimal scale parameter and the optimal shape parameter? Well, the method that's virtually always used, which has a number of desirable properties, is called the method of maximum likelihood. And here's how it works. For a particular distribution, okay, let me go down here for a minute. A gamma has a scale parameter and has a shape parameter. The scale parameter is, if you grab the tail of the density and pull it, you're kind of stretching out the density. If you push the density in, the tail in, then you're compressing it. Where a shape parameter determines the basic shape of the density within the gamma family of distributions. It turns out, for example, an exponential is a special case of a gamma where the shape is 1. So we want to estimate beta, the scale, and alpha, the shape. And what the turquoise box here says, for a particular distribution, okay, and by the way, the data are fixed. These are just numbers. You don't fit data to distributions. You fit distributions to data by choosing the parameters of the distribution appropriately. So for a particular distribution, the method chooses those values for the parameters that maximize the probability or likelihood of obtaining the observed data from, in our case, the gamma family. And let's make that a little bit more precise. Let's suppose for the gamma, you decided on 2 particular numbers, beta 1 and alpha 1, for the scale and shape. And roughly speaking, let's suppose you could compute the probability that your data came from a gamma with those values for the parameters, and it was 0.401. Wow, such a small probability. It doesn't seem very likely that the data, in fact, came from a gamma with those particular parameter values. Now let's suppose we try different values for alpha and beta, beta sub 2 and alpha sub 2, and loosely speaking, let's suppose now that the probability is 0.5 that our data came from the gamma family. Clearly, this choice would be better. Well, now you go to the nth degree, so to speak. Over all values of beta, which has to be positive, and all values of alpha that has to be positive, we're going to pick that pair of values that gives us absolutely the largest probability or likelihood that our data comes from the gamma family, and that's the method of maximum likelihood. And you would have to do it for each candidate distribution, and the maximum likelihood estimators would be different for each distribution. Okay, now we get to step 2 here, and probably don't have time for everything. Okay, so now we have these candidate distributions, and we've determined relative to the criteria of maximum likelihood what are the best parameter values. Now you've got to decide which of these distributions, if any, provides the best fit for your data. Now there isn't, once again, any definitive theorem you can find in statistics or formula that says follow this and it'll tell you what the best distribution is. So in fact, you have to use some sort of heuristic. And there are lots of possible heuristics out there. And one of the best one turns out to be what's called the test statistic for the Kolmogorov-Smirnov test. Some of you may have heard of this. It's also known as the vodka test. Ha. Okay, and the statistic is denoted as d sub n, d for distance. Here's how it's defined. What you're going to do here is going to be, we're going to compute what's called a sample distribution function. In a sense, it's another type of empirical. And it's going to be defined to be f sub n, and for a particular real number x, it's the number of x's that are less than or equal to x divided by n. So it's the proportion of observations that are less than or equal to x, and that is in fact a very natural estimate for a cumulative probability. On the other hand, let capital F be the distribution function of our fitted distribution function, like for example, the log logistic. And d sub n, which is going to be our test statistic, distance is the maximum vertical distance between the sample distribution function and our fitted distribution function. And we can see it here in this picture. Actually, I don't know if I ever maximized this. Okay, so here we have the blue is our sample distribution function for the ship loading data. It's actually a staircase, but there's so many observations you can't really see the stairs clearly. So that's F sub 856. The red line is not the log logistic here, but for making it easier to see what's going on, the red is the distribution function for the 18th best model, which is the Weibull. And you can see clearly there are differences between the two. And the test statistic for the vodka test, Kolmogorov-Smirnov, is the maximum vertical distance between those two curves, which occurs roughly for that value of x. And that value here, the length of that green line, that would be the test statistic for the Weibull. And what our heuristic is we're going to take each of the candidate distributions and we're going to compute the maximum vertical distance, and that fitted distribution that has the smallest maximum vertical distance, we'll consider that to be the best relative to this criterion of maximum likelihood. This turns out to be one of the very best heuristics that you can use. Okay, now I actually ran things through ExpertFit. ExpertFit actually uses a number of different heuristics. They're all a measure of error. For each of the candidate distributions, the distributions are ranked, 1, 2, so forth. The best distribution relative to a particular heuristic is the one that has the smallest error. So we get a bunch of rankings corresponding to the different heuristics. We combine them together, and we get these relative scores. And the log logistic turned out to be the best fit. Now, and I call this a relative score. It is best relative to my heuristics, one of which is the Kolmogorov-Smirnov test statistic. it is best relative to these heuristics among all the candidate distributions. And if you're going to use this in ExtendSim, these are the parameters you would put in. The shape would be 8.84, scale would be 0.82. And by the way, if you're wondering what a location is, most of the standard distributions like log logistic or gamma the density starts at 0. And you may want to shift it to the right, let's say 0.5 hour. In that case, the location parameter would be 0.5. Don't have time to go into this anymore. Now, let's say you use some sort of software package and you come up with the best distribution. In our case, I call it, relative score. Well, you can always come up with some best distribution relative to one or more heuristics, but that does not mean in an absolute sense that it's actually good enough to use. And ExpertFit tries to give you this absolute evaluation and gives the log logistic a good evaluation. It could also give it bad, which in that case would say use the empirical. And then there's kind of an indeterminate. One way or another, you should always do more confirmation. If you're using some software package and it spits out log logistic, viable, whatever, you shouldn't. The responsible engineer or analyst doesn't just take that and run with it. You should do additional confirmation in step 3, which is where we go right now. Okay, step 3. The classical thing to do in statistics books or a statistics course is to use a goodness of fit test like a chi-square test. To some extent, though, I actually prefer graphical comparisons, and I'll give you an idea of a few of those right here. Okay, so here's our histogram, the last one that we had decided on for our ship loading data. The red density is the best fitting log logistic. You can see that it comes quite close. And here is a crummy distribution, the 18th best Weibel. If you looked at the gamma, which I didn't put on here, you would see that it is clear. The gamma is, I don't know, maybe the 6th best. It turns out not to be very good either. So I call this a density histogram overplot. And by the way, the density or the histogram was not used to pick the best distribution. It was not one of the heuristics because it's too arbitrary. There's no definitive way to pick the interval widths. One of the main heuristics was the Kolmogorov-Smirnov statistic. Here's another one. Okay, here we have distribution functions or cumulative probabilities. The blue one is the sample distribution function. The red one is log logistic. You can see it comes very close. And the green one is the Weibel, the 18th best, very far off. Okay, I'm going to skip the next plot. You can also do goodness of fit tests, which are a more formal mechanism for testing or more formal way of testing, in our case, whether the log logistic is a good fit. And the most famous is chi-square. Basically what you do is you break your data into k intervals. Unfortunately, there's not a definitive way to pick those intervals. In this case, I picked 40. What you do is you count up how many of our observations fell in the jth interval. We're hypothesizing log logistic. You compute if the log logistic were truly correct, how many observations would we expect to fall in the jth interval? Nj is how many actually fell in the jth histogram interval, not histogram interval necessarily. We're going to break our data into k intervals. They're not necessarily histogram intervals, though, if we had time to discuss it. Nj is how many actually fell in the jth interval, k total intervals. Ej is how many we'd expect. If we have a good fit, the Ej ought to be close to the Nj. However, we do something more formal. We compute the chi-square statistic here, which for the jth interval is Nj minus Ej, quantity squared over Ej. This will be non-negative. It's a measure of error. If it's large, if it's small and positive, then basically we have a good fit. If it's large and positive, we have a bad fit. Now, the goodness of fit test, the chi-square, is just a form of a hypothesis test. We have to pick a level for our test, alpha. like 0.0, 0.05 or 0.1. Once you pick the level, you look up a critical value in a statistics book, which comes out to be 50.66 for level 0.1. We compare our statistic, which is a measure of error, to this. Big error means bad fit. So if this came out bigger than this, we would reject. Here's our critical value here. This is our rejection region. On the other hand, if our statistic falls over here, we don't say accept. We say, based on the data we have, 40 intervals of a certain size, we have no evidence to reject the log logistic. That doesn't say unequivocally the log logistic is correct. We just have no evidence. Okay. You can also do a Kolmogorov-Smirnov test. I would warn you that in many software packages and books that this is misapplied. It is not applicable to discrete data, and it's only applicable to certain continuous distributions. There isn't a KS test, for example, for the gamma, and there are different critical values for each continuous distribution for it is applicable. Okay, there's some comments about goodness of fit tests. I won't go into those because we're running short of time. You can read about these in detail in my book, and there's a picture of the book. And okay, let us now see if there's any questions. I still have plenty of time, so I'll turn it over to Dave.
Thank you, Averill. We had a couple people that had to leave, but
for the hour.
Thank you, Averill. We had a couple people that had to leave, but by and large, everyone is still here. I do have some questions for you. I'm going to try to kind of sort them into a particular order, but one came in very early, and I kind of put it off. And I think this is an interesting question. This is from Scott Burry from Dow. He says, I have seen SAS.
Oh, Scott Burry, I know him.
Okay. I've seen SAS and JUMP pushing generalized gamma distribution as a fitted function. Have you ever used this? It's not a standard random number distribution in most Monte Carlo packages or simulators.
Okay, so as far as discrete event simulation packages, for example, or if you look at JUMP, you do have the gamma. Everybody is using that. The generalized gamma, I'm almost certain, is not built into any discrete event simulation package. It may or may not be in JUMP. I can't remember. Some number of years ago, I looked into that as another candidate to be an expert fit, and the impression I got was that it wasn't going to be, that useful. I can't say that I've done exhaustive testing, but expert fit already has 40 distributions, which is quite a few. There are a number of other distributions. The generalized gamma is one of them. What else is there? No others are coming to my fingertips. JUMP does have a few other distributions available, but I just don't have them at my fingertips. I could go to JUMP here and look them up. But the best I could say is I don't think the generalized gamma is going to be that useful based on the research I did some number of years ago. But I'd have to, Dow Chemical give me a $100,000 contract to investigate it in great detail. How's that?
I think that's a fair answer.
Okay.
Something else that popped up, a couple people asked about this, is they were interested in the drawbacks of the triangular distribution, or the pitfalls of the triangular distribution.
Okay. Well, okay, I gave you two, and then I guess I have another one. One is, how do you pick the maximum? Okay. Another one is that many times I guess I could go back here and look at this. I didn't really have time to do it in detail. We can go back and look at these pictures. Okay, so let's suppose that our true underlying, let's say we're talking about a service time distribution, and say the true underlying service time distribution looks like that red density there, which is actually a log normal. Now let me assure you that this sort of shape occurs all the time. If you're talking about the time to repair a piece of equipment, very commonly you're going to have a long, thick right tail, and the log normal is going to model it better than, say, the gamma or Weibull. And let's suppose you try to model that with a triangular distribution. I'll actually go through this here a little bit. So, for example, let's just suppose this log normal distribution had a mean of 0.9, a variance of 1.39, and a mode of 2. But that's unknown, and so you're going to have to approximate it by a triangular distribution. Okay, the things that are in red are what you guess correctly. So you guess the minimum is 0, you guess that the mode is 0.2. Now how do you get B here? Well, what you do is you come up with 1.97, and the reason I picked that, it's the 90th percentile of the true log normal. 10% of the area in the tail is to the right of that. And if I go and look at what I get, okay, here is the fitted triangular distribution, and what 1.97 is, it's that value such that in the red tail you have 10% of the values there to the right of 1.97. You can see it does fairly well in the center, but doesn't do well in the tail at all. Matter of fact, you get 88% error, which I'll talk about in a minute. Okay, now you might say, he just wants to make fitting distributions look good. He purposely picked something that's horrible. Well, let's try again, see how much better you can do. Okay, triangular distribution number 2. Pick the minimum correctly, the mode correctly, and actually I picked the mean correctly. Now from that information I can get D. It turns out the mean of a triangular distribution is A plus M plus B over 3. And if you plug everything in here, the mean is 0.9, so the numerator's got to be 2.7, and it comes out B is 2.5. And if we look at the resulting triangular distribution, here's what we get. It does better in the tail, but the triangular distribution sags in the middle. Actually, I tried about maybe 4 different triangular distributions, and I could never get better than about 48% error. And more specifically, here's what I mean by that. Okay, what we have here is we have exponential interarrival times, which is denoted by M, and we have some general service time distribution, which is to be filled in, and we have one server. These sorts of queuing systems you learn about in a course in queuing theory in the university, and you can work out performance measures analytically. If you put in log normal for G, you can work out analytically the long run average number in Q is about 11. If you use the first triangular distribution, you can work out analytically that the average Q size is 1.3, which is an 88% error. If you use the second triangular distribution, you get 49% error. And like I said, I could never get anything that was better than about 48. So that's, the problem is modeling the right tail, picking V, and a third one, which may be less important, is no histogram in practice looks like a triangle. Okay, so that might be less important. Anyway, so definitely don't want to use the triangular distribution if you can collect data. By the way, in ExpertFit and in my textbook, the 4th edition, I show you how you can use either a log normal or a Weibull as an alternative to triangular if you don't have data. What you do is you get the min, most likely, and instead of the max, you get something like the 90th or 95th percentile, and you solve 2 equations and 2 unknowns. So that's in my book. Sorry about that.
No, actually, that's helpful. I probably need to read your book again, Averill. Couple more questions.
What's on page 431? Your credibility has just gone down the drain here.
Yeah, I know.
Okay.
There's a good question here, and I think you can answer as a more generalized question. Someone's asking, is there a distribution for wind or sea state?
Okay. Well, since that's not, I guess you could conceivably, even in that project we did for ConocoPhillips where we were modeling oil tankers, they get out in the ocean and they hit, hurricanes or bad weather, and that would slow down the ship. So I guess conceivably that could be an issue in an actual simulation model. Now, I don't know what distribution one would use. There is a whole book, which I have it up here on my shelf. Let me grab it here. Okay, there's a whole set of books here, and This one I'm looking at is called continuous univariate distributions. Univariate is one-dimensional. And the first two authors are Johnson and Kotz. Actually, there's about 4 or 5 books. And here in these books, they probably talk about maybe 200 different distributions, I'm guessing, and talk about possible uses of them. And just this first book here is about 700 pages long, if you can believe that. So this is kind of the definitive book. These series of books would be the ones that I would go to first. And then, of course, I would go to Google, and you might be rooted to
Averill,
that's what I would do to start out. I don't know what distribution would be appropriate in that case off the top of my head, though. And I'll say that. And probably not a normal either. Say that's very specific.
Yeah, and I've got Carson apparently knows that often these are Weibull distributions. So there's a reference I'll pass on to the question asked here.
Okay.
Another question here is let's see. I think this is the last question. Oh, 2 more questions. I find the Johnson SU distribution in JUMP and ExtendSim to be a very flexible distribution to use. Are there any caveats in using this distribution?
Okay, before I address that question, I have about 2 hours and 7 minutes on that. Let me just say that some number of years ago, I took 69 sets of data that come from real simulation projects, and I analyzed them using ExpertFit to see what distribution, which distributions fit these data sets the best. You didn't always get a good fit. What I was only looking at is what is the best fit, not necessarily good in an absolute sense. And the 2 distributions that came out the top in terms of the number of times out of 69 they provided the best fit were log normal and Pearson type 6. That hasn't come up here. Pearson type 6 is also an ExtendSim. One of the reasons that makes it very valuable is because it has 2 shape parameters. The more the number of shape parameters, the more flexible the density is. And then the next 2 best were Weibull and log logistic. And then moving down from there, there's something called the Johnson bounded distribution, which is that turned out to be fairly useful. But definitely log normal, Weibull, Pearson type 6, log logistic. Okay, now in terms of the Johnson unbounded, first of all, be a little careful in that different sources parameterize this distribution in different ways. For example, I think if you look at the definition in ExtendSim and the one in my book, they're parameterized a little bit different. So please be aware of that. Now, the Johnson unbounded distribution, one of the things that you have to be aware of is that it's an unbounded distribution. It can take on values from -infinity to +infinity. So generally speaking, the only time I've used this is on data that can take on both positive and negative values. If you were using it for something that would have to be, say, positive, you know, like the time to do something, then using the Johnson unbounded could give negative values in your simulation. So at the minimum, you would have to truncate any values less than 0. I didn't find that, you know, relatively speaking, to be, you know, nearly as valuable as the others, and in particular the Johnson bounded distribution. By the way, one thing about the Johnson bounded and the beta that are unlike all the other distributions is they're defined on a finite interval, like 2 to 5, where all these other ones like gamma, Weibull, log normal, and so forth, they're defined to be non-negative or positive. The normal, the Johnson unbounded, they go from -infinity to +infinity. So that's what I have to say about that.
One more question, and I think we'll close the questions. What is your opinion on smooth kernel distributions?
Well, I assume what's going on there, and I think this might be built into JUMP, is that rather than fit a theoretical distribution or use the empirical, you're trying to, it would be a non-parametric method. It's kind of like, I don't know, electrical engineering trying to fit a spectrum to data or something. I guess I'm not coming up with a good, the terminology I'm used to would be something like a kernel density estimator or something. And what I would do is I'd go to Wikipedia, and I'm sure it's in there. So I don't know anybody in discrete event simulation, though, that, has used that.
Yeah,
where I've seen that would be in the, the statistics literature.
Yeah, apparently it's, Carsten says it's used in Mathematica. That's nothing I've ever heard of. I have heard of Bezier curves being used, which may be similar.
Yeah. Okay, well then yet another approach, which was developed by Jim Wilson and his PhD student, I think Marianne Wagner at North Carolina State, was what are called Bezier curves. Mm-hmm. And what you basically have is some sort, and I think they're actually in Word or Excel. They actually have something like that where you can basically have certain anchor points and then kind of stretch the curve to kind of fit the shape of your histogram. And I have like one page in that on my book in Chapter 6. The problem with that, though, is those are not supported by any let's just say, any of the major simulation packages. So if you wanted to do that, you'd either have to write your own code, or actually you can go to Jim Wilson. Yeah, I forgot about this. You can go to Jim Wilson, and there is a public domain program that he has that you could get from him. So that's yet another method. But to go back to the original question, I have never heard of anybody in simulation. I've been working in simulation in 317 years. I've never heard of anybody using a kernel estimator, even though I know the general idea. I just couldn't describe it off the top of my head. And kind of like Rick Perry at the Republican debate last night.
And one other question that came in earlier, which I thought was kind of interesting, is for empirical distributions, is it possible to extrapolate beyond the last sample value?
Okay, well, amazingly, there has been some work done on kind of, okay, you have an empirical distribution, and the biggest problem is that it probably doesn't represent the true underlying right tail of the distribution. So is there some way that you could try to patch up that right tail of the empirical distribution? And what two authors suggested, and I don't see it, I think it's Bradley Fox and another book from 1987. If someone wants the reference, I can give it to them. They came up with the idea of kind of an appending an exponential tail on the right end. And there is a reference to that in my book, but the empirical studies that I remember showed that it really didn't work that well. That's the only paper or book that I know of that discusses that. So anyway, the three authors are Bradley, B-R-A-T-L-E-Y, Fox, and Schrage. I think it's S-C-H-R-A-G-E. It's a 1987 simulation book, and that exponential tail method is discussed there. I think it's also discussed a little bit in my book, but send me an email if anybody has any question about that. Matter of fact, before I forget, let me just, here at the end, if anybody wants an expert fit demo, they could send me an email, or you can go to my website and formally request one. And okay, back to the questions if there are more.
I think that's it. Thank you very much, Averill. I'm sorry that I know that our time is tight here. Unfortunately, online formats tend to make you do everything a little faster. But that was an excellent presentation. I'm getting good feedback. Some people have had to leave, but most people have actually stayed around for the whole thing. If there's any other comments you want to make, go ahead and make them, and I will end.
Well, I appreciate everybody listening, and if you have additional questions, you can send me an email. And if I can't answer it, I'm sure Dave can. Okay, thank you very much.
Okay, thank you, Averill. I'm going to end the session right now, and again, if you have questions, feel free to contact Averill, or you can contact us if you think it's appropriate for us. Thank you very much.